Hi there, it's Dimitris, and in this video, which is actually a part of a greater series of videos that I have created and are focused entirely on the AP Precalculus syllabus, we will spend a quick time to refer to a huge theorem in algebra. It's that huge that has the name, it has a characteristic referred to as fundamental theorem of algebra. Let's jump directly to it. In any polynomial of n degree, in every single function that is a polynomial of n degree, the sum of multiplicities of its roots will always be equal to the degree of that polynomial. This means, for example, that if we have the polynomial f of x equals x minus 2 cubed multiplied by x plus 1 squared, then we know that this one has the roots of 2 and negative 1. The root of 2 is of multiplicity 3. The root of 1 is of negative 1 is of multiplicity 2. 3 plus 2 is 5. So we expect that under the fundamental theorem of algebra, this function, this polynomial function, will be of degree 5. So it's going to be something times x to the power of 5. Remember, or don't remember, just pay attention on that. This theorem includes the complex roots as well. Even if the function has real roots, even if the function has complex roots, this fundamental theorem of algebra sums up the sum of multiplicities of all roots together. Let's do a quick example. The figure shown is the graph of a polynomial function. Which of the following could be an expression for g of x? What could we tell here? We can see that we have one negative root of odd multiplicity. We have one positive root of odd multiplicity, and we have one even root, one positive, root. Let's do that like this. One positive root of even multiplicity. Keep in mind, however, that we can only see the real roots on a graph. The imaginary, the complex roots do not show up as anything. Let's now go to the suggested answers. A suggests that we have the roots in A are 5 and 1 and negative 8, but all of them, all of odd multiplicity. Therefore, we should reject them. We know that we know that this should be an even multiplicity simply because the graph bounces back. Let's go to B. In B, we have the roots of negative 5, negative 1, and 8, which means that we have two negative roots. This should also be rejected. We saw, when we tried to understand the graph, we saw in details that that graph has one only negative and two positive real roots. In C, we have 5, which is a positive 1, with a multiplicity of 2. We have 1, which is a positive 1, with a multiplicity of 1. And we have negative 8, which is negative, and it is of multiplicity 1. This C could be a round graph simply because it includes one negative of multiplicity 1, one positive of multiplicity 1 and therefore of an odd multiplicity, and one positive of an even multiplicity. So these could work based on what I interpreted. Sorry about that. Let's move on. Let's see if D, however, could actually work. In D, we have one root of negative 5, which has a multiplicity of 2, And we should reject that because we know that the negative root of the graph has an odd multiplicity. Therefore, under all this reasoning, the correct answer should be C. Again, just keep in your head the fundamental theorem of algebra. If we have a polynomial of n degree, then the sum of the multiplicities, not the sum of its roots, the sum of the multiplicities of its roots should always add up to that polynomial's degree. That was all. I hope I made things more clear. If you like this video, if you found it helpful enough, don't forget to like and subscribe. As always, thank you for watching and thank you for spending your time. Have a good day.